Scatterplots, sweet scatterplots. Um, Here we are. We're finally done. We're putting descriptive statistics behind us. We're moving on to a new section, to a new topic. It may at first seem like a little bit of a jarring transition, but I assure you it actually transitions fairly smoothly from what we talked about. Everything we've talked about previously is what we might think of as univariate descriptive statistics. So univariate as in one variable, a single variable, right? We talked about the mean, the median, an average for a single variable, right? Like the salary of a nursing major. We talked about standard deviation range, again in the context of a single variable. Even looking at things like weights of walruses, right, and z-scores, we were still looking at a single variable. What we're getting ready to do now is still kind of focus on this idea of descriptive statistics, but now we're focusing on this idea of descriptive statistics in what we would call a bivariate world. So now instead of a single variable, we're going to focus on two variables. And the characteristic that we're going to be trying to describe is the potential relationship between these two variables. All right, so here's a little bit of light lifting, maybe a little bit of deja vu. We kind of talked a little bit about this kind of stuff earlier when we talked about experiments, experimental studies, observational studies. As you may remember, we talked about this idea of an explanatory variable, a response variable. We even talked about something called a lurking variable, which is going to be on the next slide coming up. And so a very, very common problem for researchers in any field of study, particularly the field that you're studying, is to test whether or not, right, there may or may not be some relationship between two variables. The one that's doing the explaining, we call that the explanatory variable. The one that we think is being explained, we call that the response variable. The example on the slides coming up, it's actually kind of some light limbering up exercises. It's an example that we've already seen and talked about previously. The second bullet point on this particular slide, I guess, is a new example, somewhat straightforward. Right, we might be interested in whether or not there's a relationship between a person's height and a person's weight. Maybe a little bit of a trivial, uninteresting example. It's just our training wheels, beginner's example. Hopefully we buy into the fact that there is a relationship, right? The taller someone is, the more they tend to weigh. Certainly exceptions to that rule, but by and large, that's what we tend to see. If I told you that I had two friends, one of my friends is 7 feet tall, one of my friends is 4 feet tall, and I asked you to guess which one of my friends do you think weighs the most, probably most of us would pick the 7 foot tall person. That would give us sort of the highest probability of being right. Is it possible that we're wrong? It's always possible, I suppose. But most likely we're going to be okay. That is, I think most 7 feet people weigh more than most 4 foot tall people.
Now, in addition to these explanatory and response variables, we have these things called lurking variables. So, right, with the idea of explanatory and response, we basically have one variable. The explanatory variable influences, explains the other variable, the response variable. We often call the explanatory variable x. Makes sense because there's an x in the word explanatory. We often call the other variable, the response variable, y. So the lurking variable is any variable other than x that also helps explain y. Here's maybe a slightly more interesting real-life example. Right? Say we're maybe interested in doing a study. Obviously, lots of studies have been done on this, in determining whether or not a vegetarian diet helps reduce heart disease. So imagine a study like that. The explanatory variable in this example would be diet. Right? We're basically interested in whether this presence or absence of meat, whether a person's vegetarian or not vegetarian, is going to explain the response variable. The response variable being a person's heart health. We didn't really get into the specifics, but maybe we can measure it by number of myocardial infractions, some kind of percent of plaque buildup, maybe just something a little more simple like your systolic blood pressure or just your overall pulse. Um, we But in addition to these two variables that are kind of the focus of our study, there's lots of other variables, and this is generally the case. What are some other variables, right, other than diet or right, vegetarian or non-vegetarian, that might also explain our overall heart health? Well, right, genetics plays a big role in how healthy our heart is. Whether or not we smoke plays a big role in how healthy our heart is. Other aspects of our diet, right? You could still be vegetarian and just eat Cheetos and ice cream all day. May not be healthy. Right? How much we exercise, how much we drink, and I'm sure if you really think about it, you can come up with your own examples of things that, in addition to presence or absence of meat, may also explain our overall heart health. Now, when we're interested in exploring relationships between these two variables, between x, between y, between the explanatory variable and the response variable, now the first thing we generally do is we start with some sort of plot. This parallels kind of how we started at the very beginning of this course, in terms of, right, when we're looking at a single variable and describing its behavior. We started by looking at plots, things like histograms, things like stem plots. And then we went on to look at things like means and medians and standard deviations. We're going to do something very similar here. We're going to start with plots, and then we're going to look at numerical measurements. For now, the appropriate plot when you have two variables is called a scatter plot. So a scatter plot graphically shows the relationship between two quantitative variables. They both have to be quantitative. And they're also measured on the same individual. Now this is just like plotting points in like your algebra class. What you basically do is each individual appears as a point in the plot, right, in this sort of xy coordinate plane. Generally, the explanatory variables on the x-axis, the response variables on the y-axis. So say that we're interested in testing our claim that a person's height predicts their weight. We go out, we sample some kids. We measure the heights of all these kids, we measure their weights, and not sure how realistic these numbers are, but I don't know. They're maybe a little bit reasonable if we don't look at them too closely. And so for each person, right, we have two numbers. So the first person is 60 inches tall, weighs 110 pounds. We can plot that. Next one is 61, 105. We can plot that. We can do this for all 10 children. Now here's a plot that I did on my computer really quick using something called SAS. You can do this on your calculator. I would just say, in class I would just do this on the whiteboard and have you do it on paper. It's a relatively simple plot to make. So at some point, make sure that you compare this graph with the numbers on the previous slide and make sure you understand how we get from one to the other. We can see the person who was 60 pounds and 60 inches and 110 pounds. They're sort of the leftmost plus. That's still pretty low. And notice that they all seem to follow a pretty orderly pattern. If you look at 69, there is a kid or someone who's 69 inches tall, and you go up and they weigh 200 pounds. So we have a bit of maybe an outlier there, something kind of outside of the pattern. But other than that one person, they all do seem to follow a pretty orderly pattern. Let's talk more about that as we kind of go through our next few slides. More specifically, what is it that we really want to look at when we look at a scatter plot or a scatter diagram? Well, these things are really good for describing three things about a relationship. One, they're very good about describing the form of a relationship. Two, they're very good at describing the direction of a relationship. And three, they're very good at describing the strength of the relationship. What do we mean by all these? Well, by form, we look at overall shapes. Is there some sort of curved shape? Is there some sort of linear line shape? Is there no shape at all? Or is there something maybe more complicated, some sort of maybe oscillating pattern? What about direction? That's basically saying, is this a positive association, or is this a negative association, or is there no direction? Is there no association? Um, Now notice that direction generally is referring to straight lines. And the last is strength. The strength basically says, okay, the form that you picked, how tightly packed are the points about this form? Right? Are they spread out or are they very close together? That's the idea of strength. So forms, right? We have sort of lines. We can think of examples of that. Probably we'll look at an example in a second. Curves. Sometimes things follow a curve pattern. So for instance, someone showed once that if you look at basketball players, and for every retired basketball player, you record two things. You record their height, and you record their age of retirement. And you make a plot. The x-axis is height, the y-axis is the age that they retired. You see this sort of curved pattern, a curved pattern that would look like a frowny face. That is, as your x increases, as your basketball player gets taller, for a while at least, they tend to be able to play the game longer and longer. That is, their age of retirement goes up and up and up. Which makes sense, right? Because height is something that's useful in basketball, and it's something that, unlike your reflexes, unlike your eyesight, unlike your accuracy, doesn't deteriorate with age. So if you're really tall, that's a good skill, lets you play longer. But at some point, and I think this was right around 7 feet tall, at some point you become so tall that you become sort of injury prone. That is, running up and down and up and down and up and down this basketball course just does so much damage to your body that you end up sort of destroying yourself. And so right around 7 feet tall, think of the great Yao Ming, you start seeing lots of injuries, and that age of retirement starts to go down and down and down and down. So there are complicated relationships that have this curvature pattern. They're not the focus of this class. They're sort of more complicated for this class. We're going to really focus on either linear patterns or no patterns at all. But do keep in mind that these lines that we're going to focus on, they're certainly not the only type of behavior out there. The other type of scatter plot, the final one, is where there's just sort of no form at all. Imagine if you did a plot where x is like the length of somebody's hair, y is their IQ. You would imagine that there's just sort of no pattern whatsoever. You just had dots or pluses everywhere. What do you think the form of this is? Right, this is going back to our height and weight example. How would you describe that? Yeah, I would describe it as a line too. It looks like it has a very, very linear pattern. Sure, you can't make a line that hits all the points, but with the exception of that 200-pound person, excuse me. With the exception of that 200-pound person, everyone seems to be really tightly packed about a line. What about the direction of a relationship? We talked about two different directions, or at least mentioned them, positive and negative. Now this kind of also goes back to math class. You could think of this as like positive slope of a line and negative slope of a line. A positive relationship basically says that as your x increases, your y sort of tends to increase, or you would expect it to increase. You could also say it in I guess the opposite way. As your x decreases, you expect your y to decrease. So a positive relationship basically just means that x and y travel together. One goes up, the other goes up. One goes down, the other goes down. A negative relationship is the opposite of that. As your x increases, you sort of expect your y to decrease. Alternatively, as your x decreases, you expect your y to increase. So a negative relationship is sort of antagonistic. As one increases, the other decreases. As one decreases, the other increases. They do the opposite of one another, presumably just to spite each other. That's what I would call a negative relationship. What about here? What type of relationship do you think you would use to describe that? Yeah, I think I would call it a positive relationship too. That we see this this sort of positive association. As a person's height is increasing, their weight tends to be increasing as well. Again, if we were to draw a line that is really close to those points, that line would have positive slope. It's an analogous idea. Now, the last thing that we look for in scatter plots, and this is the most subjective of the three things, is the strength of the relationship. A strong relationship, all the points are packed very tightly about that line. A weak relationship, all the points are really diffuse, really spread out from that line.
All right, so back to our height and weight example. Here's our scatter plot, yet again. This is actually a very, very strong relationship. In fact, in real life, it's rare to see such a strong relationship. Now, as a potential beginner, as a student, you might have said that it's medium strength. Who knows? You might have even said it's weak strength. It's difficult to sort of put these labels on a particular scatter plot, right? Particularly when you're beginning and you haven't seen a lot of these things, so you have no sort of comparison point, right? Strong is a relative term. Strong relative to what? Right? I've seen hundreds, if not thousands, of these things, so I could say this is very strong relative to many of the scatter plots that I've seen throughout my day-to-day practice. If you look in the textbook, and again, hopefully you're reading along with the textbook, it's a pretty good textbook. The textbook has lots of pictures of scatter plots and shows you this is what a weak one would look like, what a strong one would look like, and so forth. So make sure you look at the scatter plots in the textbook for some kind of additional examples. Now that said, even for for master level black belt statisticians and researchers, if you take a scatter plot that has hundreds of observations and you put it side by side with another scatter plot that has hundreds of observations and you look at it, it's sometimes difficult, often difficult, to sort of eyeball them and say, okay, this one's stronger than the other, right? That is, even for an expert statistician, there's subjectivity in terms of trying to say, right, well, this relationship seems stronger or weaker than that relationship. Just like before, we have a graph, we have a visual summary. That visual summary does illustrate a lot of points, right? It illustrates a lot of information. We have, at this point, this sort of strong positive linear relationship between height and weight. There's a lot of information we can see quite clearly. Nonetheless, particularly when it comes to talking about the strength of the relationship, it would be nice to be able to talk about it a little bit more concretely, a little bit more objectively. It would be nice if we could actually in some way quantify or measure that strength. And that's exactly what we're going to do in the next few slides coming up.
This measurement is called the sample correlation coefficient, abbreviated with just the small letter r. That makes sense, I guess, because there's two r's in the word correlation. Now, this correlation coefficient r, it's a numerical measurement of the strength and direction, but it only applies to linear relationships. We'll talk a little bit more about this towards the end of the PowerPoint. Some facts. R has no unit, which kind of makes sense, or at least is maybe reassuring, because what would the units be? Think back to our example of inches and pounds. Is it inch pounds, pound inches, inch pound pound? Right? It's hard to even think of what the units would be. It turns out that there are no units. So R is kind of a somewhat rare statistical measurement that has no units attached to it. R also takes values from -1 to 1. If someone tells you the correlation is 3, you say hogwash, correlation can't be 3. Can't be more than 1. Someone tells you the correlation is -1.2, you say balderdash, correlation can't be -1.2. Has to be between -1 and 1. If R is negative, then that implies a negative linear association. So if R is negative, it applies a negative association or relationship. If R is positive, it indicates a positive relationship. So that's pretty intuitive, right? That this correlation, basically whether it's positive or negative, also tells us what the direction of the relationship is. If R is 0, there's no, and I should emphasize this, there's no linear relationship. The closer R is to 1 or -1, the stronger the relationship is. So this is a way of measuring strength. If something's really close to 1, it's a strong positive relationship. If something is really close to -1, it's a very strong negative relationship. Another really fun fact is that correlation is the same regardless of which variable is the explanatory one and which one is the response one. That is, if you went back to our original graph, if instead of having height on the x-axis you put weight there, and you put height on the y-axis, it wouldn't change the correlation. That is, you would get the same correlation. You'd sort of be describing the same relationship. Also, the value of r doesn't change when either variable is converted to different units. That's also intuitive. I mean, we would expect like the same fundamental biological relationship between height and weight, regardless of whether we measure it here in inches and pounds, or we measured it in England in, I don't know, meters and or meters and stones, maybe, meters and kilograms, whatever the appropriate units would be. Turns out units don't matter in terms of calculating the correlation. Now here's a formula. Our book probably does lots of examples calculating this. I'm not going to ask you to on a test. You won't be asked to calculate on a test. I don't know if you will on a quiz or not, but for your quiz you'll have your book and your calculator, so if you had to, it's not that big a deal. But I wouldn't ask this on a test. Certainly wouldn't ask you to do it by hand. It's very painful to do by hand. In practice, it's done in Excel, it's done on a calculator, it's done using a statistical program like SAS, but here's the formula nonetheless. If we took the points for our height weight data set and we ran it through a calculator and it used that formula from the previous slide, that is, it multiplied, divided, added up a whole bunch of stuff, we would basically get a correlation, positive. We expected that, right? Because we said it was a positive relationship close to 0.8. That is, that 0.8 is indicating a pretty strong positive association. Hey, here's a question for you. What do you think would happen? You remember that 200-pound person in our sample? What do you think would happen if we removed that person and recalculated the correlation? Yeah, I think so too. I think that what we would see happen is that correlation would become, it would still be positive, but it would get even stronger, right? Because with that point gone, all the points now are even more tightly packed about that line. And so our correlation would go up. I always keep meaning to recalculate to see what it would go up to, but I wouldn't be surprised if it went from like 0.8 to 0.9. That is, if it made a pretty big jump in terms of its strength. Which leads us to this observation, that correlation is not a resistant measurement. That means that it can be strongly influenced or distorted by extreme observations. That is, just a single point, a single 200-pound individual, even though they're only sort of 1/10 of the sample, right, 1 out of 10 people, can sort of exercise an undue influence in terms of the actual correlation. That is, removing one person can drastically change it from, say, 0.8 to something like 0.9 or 0.95. Just out of curiosity, what do you think would happen? We have our correlation now. Our correlation, right, was 0.7999 something. Let's call it 0.8. If instead of testing whether a person's height can predict their weight, we want to test whether their weight can predict their height, what would the correlation be then? Of course, we said this like 4 or 5 slides back. It's going to be the same. It doesn't matter if you switch your x and y. What's the correlation if we measure the weight in kilograms instead of pounds, and we measure the height in meters instead of inches? That's right. We said that a few slides ago too. It actually doesn't make a difference. The correlation, again, stays the same. It's still 0.8. Now, a few cautionaries. A really strong correlation doesn't mean that there's cause and effect. You might see a question on this, like this on your test. Always use common sense when interpreting these things. So, it's probably true that if you went through like the last 100 years and you measured say the amount, the dollar amount of charitable donations, say in Philadelphia, and some measurement of crime, I don't know, maybe robberies per 1,000 people or something like that, you would see a positive relationship. That is, you would see, say, for the year 1950, you might have x is 5 and y is 7, and then 1951, you'd see x goes up a little bit, but y goes up a little bit too. And then in 52, your x goes up also, your y also goes up. So we see, like, when x is small, y is small. When x is large, y is large. It's a positive relationship. We'd probably see it's pretty strong too. That is, a plausible correlation might be something like 0.78, which might lead a naive statistician to conclude, wow, there seems to be this really strong relationship between how much we donate and how much crime there is. So maybe if we all make a pact, hey, let's all agree to just stop donating, maybe we could save the world. Maybe we could eradicate crime. It's nonsense, right? Well, then why do we see that correlation? Well, it goes back to what we talked about at the very beginning of this PowerPoint. It goes back to these lurking variables. Right? It may not be x that's explaining y. There might be some third variable. What's the third variable in this example? That third variable is, you can think of it as time. Probably a better way of thinking about it is population, right? Over time, the population in Philadelphia has been growing. When there's more people in Philadelphia, we see more money being donated and more crime. Right? So the crime probably has nothing to do with the charitable donations. It's just that both of them are going up. They're both being driven up by this third lurking variable, population. Always temper your conclusions with common sense. Oh, this is what we just said. How do you like that? We must be cautious even when a correlation is strong and concluding that the explanatory variable causes the response variable. Sometimes their behavior is related through a third variable. And our last warning, right, r equal to 0 doesn't always mean that there's no relationship between the variable. It means that there's no linear relationship, which is why in practice you don't just get the data and calculate the correlation. In practice, in real life, you get the data, you make the scatter plot. You look at the scatter plot. If it has a linear shape, then you do the correlation. If it doesn't have a linear shape, you have to do something a little more sophisticated. Now, I always kind of use this example in class. X, the amount of time spent studying. Y, the grade on a midterm. I say for a while it goes up. That is, the more time you spend studying, the kind of higher you might expect your grade to be on the midterm. At some point, it starts to kind of flatten out. That is, if you've already studied 30 hours, studying another hour is probably not going to do much for you. And at some point, it might actually even be the more you study, like the lower the grade you could expect to get on your midterm is, because, right, there's only so much time in the day. You also have to eat, you also have to sleep, and I do see students every once in a while. They come in all crazed and shaking, and they have a Rockstar soda in one hand and a Rockstar soda in the other hand, and they're double fisting it. They're like, man, I've been up all night studying, and that's generally a bad idea, right? So a good night's sleep is also important. And so in situations like this, where you have that sort of that curve pattern, that frowny face pattern, what you see is, well, for a while it's increasing, and for a while it's decreasing. So for a while you have this sort of positive correlation, and then for a while you have this negative correlation, and they tend to cancel one another out and give you a correlation of 0, which is sometimes misinterpreted as no relationship, when in fact it's really just saying there's no linear relationship. I think this is about everything you need for correlation. The book also talks about this thing called a coefficient of determination. That'll be talked about in the next set of PowerPoints.